Okay, this is lecture 17 and this is the last lecture for our discussion on the power. So let's go to our previous lecture. So lecture 16 was devoted to the dynamic power consumption. So dynamic power consumption was given by this seemingly quite a simple form. So here we have activity factor and capacitance and square of VDD and operational frequency. So we have studied various ways to reduce the switching power. So now let's go to this static power part. So static power means that for example, when you consider inverter here, then in ideal case there is no static power consumption. So we have studied up to now in that way. So for example, either we apply 0 volt or VDD volt, then the output will be either VDD or 0. Yes. So in this case, we can find one of our transistor is turned on and one of them is also turned off. For example, when you consider this VDD case, then this is on and this is off. So although this N MOSFET is turned on, since P MOSFET is completely off, so the current flowing through this current path from VDD to ground vanishes. So that is our common discussion about this static power. So good, so really good in terms of static power when we consider CMOS circuit. The point is, so we have made that assumption. When we turn off our transistor, for example P MOSFET, by applying VDD, so we have actually 0 VGS, VGS equal to 0 volt, then we assume that the turning off is quite complete. I mean that there is no real current at all here. So that's the reason why we have although our N MOSFET is turned on, the overall current becomes 0. However, we have already studied that when we draw the realistic IV characteristics of our transistor, for example in the case of N MOSFET, we can draw in this way. What happens if we draw actually in the logarithmic scale log 10, then in this case our graph just looks like this. Maybe you remember this curve. Yes. So of course our VDS equal to, in this case VDD, we have driven our drain terminal quite a high amount of voltage, and here we have certain current called as I off current. Of course here we have I on, but our current interest is laid on this one. This current simply means that even though we apply the 0 volt to our gate, but the transistor still conduct a little amount of current. So let me just come back to our inverter case once again. Let's think about this particular situation. We have applied 0 volt to the common gate. Then now we can understand this P MOSFET is completely off, and here we have on, and N MOSFET is completely off. So ideally, the drain current in our N MOSFET should be 0. However, you know that it is not exactly 0 in reality, but it is just given by off current. So you can easily understand this P MOSFET can drive I of current. Of course, here we have completely turned on P MOSFET, so voltage at this point is slightly adjusted to conduct this I of current even in the case of our P MOSFET. For P MOSFET, conducting this small amount of current doesn't matter because it is already fully turned on. So very small deviation from the perfect VDD will allow this small current conduction. So still we can treat it as very good VDD, strong VDD. However, the overall current will be just determined by what? Determined by the off current of our serially connected transistors. Okay, so now we have constant I/O through these serially connected transistors. Then our question is, what is power consumption at a given time? Let's say that we just keep this input voltage as 0 and output voltage as VDD, but still we have power dissipation. Power dissipation is given by a product between current and voltage is always VDD. That doesn't change. And how about the current? Current is of current of, in this case, N MOSFET. So this product just gives you the power consumption. Although I have explicitly shown the time dependence here. However, you know, this is a constant and this off current is also a constant. So we can think that this power consumption is steadily there. So even though we do not switch our transistors, still this amount of power consumption is always there. Now everybody understand, compared with this, for example, when you charge your load capacitor, then you up to 0 to VDD, we have to supply the amount of charge like C times VDD. This amount of charge, and compared with this IOP, they have a different unit. This is charge and this is current, and when it is integrated over certain time interval, then it becomes charge quantity. So therefore, if we integrate a certain time, then we can find certain power energy dissipated during that time period starting from 0 to t. That will be the energy dissipated during the time interval from 0 to t. So then we can make a comparison between this switching power consumption and static power consumption. The reason why we call it as static power consumption is, although we do not switch our transistors or our logic gate, but it is always there. It means that even though we do not process our signal, our information, but it is just spent in this time. Let's say that there is a person, he or she can learn, speak, and jump, whatever, study. So there can be very much action. So, however, let's say that this guy give up every action and just stay or lay on the bed and do nothing. Just breathe. Then what will happen? Since he or she doesn't do anything, so after 1 day later, what will happen? 1 day later, how about the weight? Starting from, for example, 70 becomes just 70 due to conservation of mass? Of course not. Although nothing happens, nothing active happens to this guy, but in order to just maintain the life, there is a certain amount of energy just spent by this guy. So quite similarly, this steady power consumption is just like that. Oh, we do nothing. We do not process any meaningful information, but in order to just turn on the gate, we must spend such kind of power. So I think that it is kind of a wasted energy, just stand by. So static power is consumed even when a chip is not switching. So everybody understand, and it can be represented by this way. We have VDD. Yes, we have VDD, and from the viewpoint of VDD, any kind of current conduction, so VDD, and here we have ground, and any kind of current conduction will contribute this static power consumption. Okay, so that is quite obvious. So here if we have a certain kind of I, then from our battery VDD, then the amount of power spent by our battery system will be given by I. Then our remaining concern is how can we calculate or estimate this I current in this system. So in the case of our CMOS circuit, okay. In the case of our CMOS circuit, when our circuit is in the steady state, then actually some of them are turned on and some of them are turned off. So it is quite obvious. And here you are now looking at two different cases. Here we have N MOSFET is on, and here you have P MOSFET is on. However, in both cases, there is no current conduction. Always it is compensated by this turned off device. So now you can understand, in any case this current is nothing related with this on current. On current doesn't matter because we have pull up network and here we have pull down network, and in our CMOS circuit in its steady state, once only one of them is turned on and one of them is turned off, or this one is turned off and this one is turned off. So from the viewpoint of our VDD, the path toward ground is always disconnected by this way or disconnected by that way. So everybody now understand the current will be here. When we say that current, this current will be the off current of turned off network. Okay, so then how can we consider this current? So transistors can contribute many different components, but for this case, please do not consider this contention current. This is not for our CMOS logic system, because up to now we have all considered such kind of CMOS circuit which has two complementary circuits like a pull-up network and pull-down network, so no direct current path is allowed. However, for some logic families, so the direct current path is available, so that is related with this contention current is related with those kind of logics. Okay, so not that interested in our CMOS implementation. Then now let's go to other three part. Other three part is given by this I sub is subthreshold current. So this is nothing but the current I always draw in this way. This is the subthreshold current. Yes, I'm now talking about this one. Our I op is actually the subthreshold current. Means that we have applied relatively low gate bias and drive our drain with a high voltage, then there will be certain current conduction. That is our subthreshold current. And another component we have not considered up to now is gate current. So gate current means that, let me just explain for one. So now think about this case. Here, now we have a transistor, and let's say that we have applied, for example, very high voltage, and drain is seemingly very small. You know, this is quite a typical situation we can observe in the case of a CMOS inverter or CMOS circuit. Then, wow, now think about this one. Usually when you consider leakage current, what you consider is like this. You usually consider the case like you apply 0 volt and drain is VDD. So say that this transistor seems to be completely turned off. However, there occurs small leakage current between its drain and source. That is the typical way we consider this leakage current. So that is the case. However, when we consider this, the opposite case, now gate is highly biased and drain is lowly biased. So in ideal case, since drain voltage is exactly 0, there will be no current conduction between source and drain. Yes, it is diminishing. There is no component like that. But point is, since we have very high gate voltage, so please concentrate on this part. This is a little bit different from our discussion of now. Since gate voltage is so high, so we can consider another conduction path from here, from our gate. So how that can happen? So up to now, we always assume that this oxide is a perfect insulator. Up to now, that is perfect insulator, So we have no chance to make current conduction through this perfect insulating layer, silicon dioxide. However, in reality, this is not perfect insulator. Although that is quite good insulator, however, it's not perfect. So, in this case, we can have gate current. Gate can contribute a certain current into the channel, and obviously, depending on the bias condition, that can be either flow into source or either flow into the drain. So this is the second mechanism called as gate leakage current. And another one is a junction current, and junction current is nothing but the PN junction current. So where do we have a PN junction? So once again, let's consider our MOSFET. So when we have inserted our MOSFET here, now we have a certain drain and certain source path, and of course here we have p-type substrate. So usually what we do is apply certain positive bias to our drain, and substrate is grounded. So p-type is grounded and n-type is positively biased. What is it? In this case, our PN junction located here is reverse biased. When we have reverse biased PN junction, then we can have small amount of current conduction. That is considered here as a junction current. Okay, so now you understand these three components are coming from the imperfection of our transistors. If we can make our transistor perfectly good, then there will be no such kind of current conduction mechanisms. However, unfortunately, we are not perfect, so we have to understand there may be certain amount of leakage current. And I think that this is taken from the source, certain news magazine about semiconductor engineering, and this slide just compares the amount or relative magnitude of dynamic power consumption and static power consumption. When you have a look at this chart, then if we go to a more advanced processor nodes, then dynamic power consumption is growing. Yes, that is growing, but its its growth rate is not that high. Instead of that, this leakage current is rapidly increasing. So previously, when technology was lowly developed, not that much advanced, so the leakage current or static power consumption was much lower than this dynamic power consumption. But nowadays it is getting more and more important to consider leakage current. So also that is related with one thing. So we are now living in the mobile era, so we are really critical about the battery life. So that's the reason why static power consumption is just done without doing anything. So if you have a cell phone and if you just turn on your cell phone, do nothing, not gaming, not making any chat with your friends, but still it will be eventually the cell phone will be turned off. That battery life is determined by your static power consumption. Okay, so then let me just give you an example taken from our textbook. Here we have 1 billion transistors just in the previous lecture. And let's say that we have a small amount of 5% of logic transistor and 95% of memory transistors. And let's say that all of our memory transistors have relatively high VT. So when we say a transistor has high VT, what does it mean? So when you draw ID versus VGS curve, our VT just determines the knee point between this more or less saturated current or high level of current and rapidly decreasing current. So, for example, say that this is about threshold voltage. Beyond this threshold voltage, our current does not increase rapidly. However, below the threshold voltage, our current rapidly decreasing. So now let's think about two different cases. You have a similar technology, so from a given technology, but you have two different options. One is your threshold voltage is relatively low, and the other one is your threshold voltage is relatively high. Then what will happen to your output current? You know, below threshold voltage, you have exponential decreasing current here. So now you can understand this current or this slope is given by what? Given by so-called sub-threshold slope. And also it has also given by this slope is given by sub-threshold slope. So since they are coming from the same device or same technology, so let's assume that sub-threshold slopes of these two devices are the same. Then what will happen? Starting from similar level of current and decreasing the same slope, then when we measure the current at 0 gate to source voltage, now you can see that for low VT transistor, you have quite high I/O current. And when you have relatively high threshold voltage, then you can say that your off current will be quite low. So simply speaking, when you have high VT, it is corresponding to low I of current. On the other hand, if you have relatively low VT, then that is corresponding to relatively high I of current. So once you understand this one, then let's revisit our example once again. Now 85% of our transistors, they are assigned to the memory operation, and they all have high VT in this example. Then what does it mean? They do not spend much leakage current. And in the case of logic gate, 5%, 50 million, and among them, only 5% of them has relatively low VT. They are assigned to this technology because they are really performance critical path. So 5% of our transistors are assigned to the most powerful job, and for all other 90% of them, they just do the conventional job, not that much performance hungry, so they have relatively low. So now can easily calculate the total width of your transistors. So low VT transistors, how many transistors are there? In the case of low VT transistor, there is 50 million logic transistors. However, only 5% of them they have low VT cases. And how about high VT case? In this case, all memory transistors and 95% of our logic transistors are used with these high VT transistors. And now let's assume that subthreshold leakage current, low VT1. So you know your VT is low, so it is regarded as a high performance, and in this case, unfortunately, you have high leakage current. Then now you have a relatively high value. And for high VT1, that is more energy efficient one, then you have relatively low leakage current. So now you can easily calculate this number. How can you calculate this number? Since you have total width like this, so calculate 100 nanoamp per micrometer. This is the leakage current per unit width, and this is for your low VT. And for your low VT case, you have 0.75 times 10 to the 6 micrometer. This is a contribution from your low VT transistor. And you know, you have also 10 nanoamp per micrometer times this number, 109 times 10 to the 6 micrometer. This contribution comes from your high VT transistors. Okay, are you all with me? But when you just calculate it in this way, then your answer will be much larger than the correct answer. We need one more. So now let's come back to our inverter in this case. Okay, so anyway, so let's just go to the next part. So without spending our time on this second one. So now let's go to more realistic cases. So this is taken from Intel's more than 10 years ago IDM abstract, and I think that we have already seen it before. And at the time I told you that how can we distinguish different transistor options. Then I hope that now you can understand it much better than that. Now please have a look at this off current conditions. So now you can see that in terms of milliamp per micrometer. So now here you can see that this one, this one here you have this is this family are reserved for high voltage operation, for while just to concentrate on these logic families, high speed logic and low power logic. In this case we have four different devices, and you know that their current options are given here: 100 nanoamp or 1 nanoamp. So this is quite small, and even smaller we can find 30 picoamp or 15 picoamp. So you know this is the variation we can have 10 years, more than 10 years ago, and nowadays we can have even more numbers of device options. So usually, how can we make such kind of so many different options? So that is more or less related with splitting the threshold voltage. So in many cases, they just share the same curve. However, by just changing their threshold voltage, then what the engineers can do is just to shift it to this way or shift it to that way. Then what will happen? By shifting the threshold voltage in this way and that way, we can introduce a drastic change in the eye of current and slight increase or slight decrease in our own current. So are you with me? So now you can provide many different options for this device. Your op current performance is excellent. However, unfortunately, your device suffers from relatively low performance. On the other hand, if you have this device is really good for high performance computing. However, it spends a lot of static power consumption. So you must select the right place for right transistor. Okay, now this is the way we do. And my final comment on this one, threshold voltage. Then maybe you can ask me, how can we control the threshold voltage? So I just told you like a magic, engineers can do that. But how do our engineers change the threshold voltage? It is usually done by making certain engineering on the gate stack. So everybody understand transistor has some kind of stacks. Here we have a metal and here we have a dielectric layer, usually called as oxide layer. They do something in this part. Then changing the fabrication procedure, then they can control the threshold. So that is well known in the industry. Okay, so up to now we have studied the terms like static power consumption and their origins. So what is the origin of these transistor leakages? So we have identified more or less subthreshold current and gate leakage current. Two are most important one. Of course, here we have junction current, but importance of junction current is relatively low compared with this subthreshold current and gate current. And what I wanted to say is, for most of state-of-the-art device, the most important one is still this subthreshold current. Yes, this is quite important. That's the reason why we always draw this graph and we are much care about this subthreshold current. This one really almost determine the static power consumption, and static power consumption is really important to consider the overall power consumption. Here we have a simple but useful relation for subthreshold current. Here we have gate dependence and drain dependence. So please only think about the gate dependence. Then it is given by I of times exponential Vt over sorry, V O. Okay, so once again pencil is stopped, so let's wait for a while and it will be recovered. Okay, then here we have VGS. This one is written as a here in this way, introducing this subthreshold slope S, so they are identical. Although here we have base of 10 and here we have a base of natural number E, but since we have S here, so they are identical. So simply speaking, in the case of our so of course here we have some number n, but please understand this one. When we have this gate dependence, it is exponentially increasing. Yes, we know it. And another dependence is related with this one. This expression is best sheeted when we have VDS equal to VDD. Then what will happen? In this case, this difference becomes just 0 and no impact. However, if we have a condition like our VDS is lower than VDD, then of course our subthreshold or our leakage current will be decreasing. Then now it will be a negative number and it will give us a slightly reduced subthreshold current. And here we have also body source to body voltage, so that will be also considering here. So and please note that this eta and k, these are values much smaller than 1 and they have a positive value. Okay, so now then think about sorry, so pencil is once again stopped, so let's wait for a while. Okay, cool. Now think about the case like this. Here we have the dependence like V, S, B. Source is, let's say that, grounded, and body. Usually body is also grounded, but sometimes we can introduce intentionally certain negative voltage to this body. So are you with me? In that usually we have source and drain and this is grounded. Let's consider this case. However, in order to increase our threshold voltage intentionally, we can apply negative voltage to the body contact. Then what will happen? Since the reference is body contact, then now it becomes, when we apply negative voltage to our p-type substrate, now it becomes positive. When it becomes positive, you can see that also this one will give a negative number, so we will have decrease of our subthreshold leakage current. It is quite much acceptable because, when you apply your p-type substrate to a negative voltage, then you can expect your threshold voltage is now increasing. So therefore, since threshold voltage becomes higher, so you can understand your op current is reduced. That is expressed by this term, substrate dependence or body dependence. Okay, so now we will understand this case. Then here now you have Now, in this serially connected two MOSFETs, two N MOSFETs, here we have, it has its own body and it has its own body, of course, but it is assumed that their bodies are connected to the ground. That is quite a typical cases. So then let's consider what will happen when we have the Vx voltage equal to 0 volt, then there will be nothing. So this N2 device, if Vx equal to 0 and its body voltage is also 0, so its Vx is equal to its source voltage, then source to body voltage will be 0. Nothing happens. However, instead of that, now think about another case. What happens if this Vx equal to Vdd? Then, if we have this kind of situation, then our source to body voltage will be just Vdd. So, although this is Vdd, this is body is grounded, now consider this becomes Vdd. How can we generate or consider such a kind of situation? And in this case, what we can do is we can apply, for example, 0 volt. And for example, if we instead of that, if we apply Vdd, then what will happen? Since this device is now on, this is off, so now we have this relative, not exactly Vdd, but that will be increased. So that can happen to this case. So simply speaking, by the action of our transistor operation, this source voltage is not always equal to 0. It can be increased. So of course its value will be bounded between 0 to Vdd, and in this case we will have certain elevated voltage, and for this N2 device, since its body is grounded, and it will have relatively high Vt. So then our next question is, now we have two different devices, one device and another device, and let's say that this one has relatively high Vt and this is relatively low Vt. What does it mean? So this one has relatively low leakage current and this one has a relatively high leakage current, and they are serially connected. What will be the consequence of this serial connection? Which one determines the overall leakage current? So please think about our NMOS, our inverter once again. Here we have transistors, and yes, say that this is off and on. Which one determines the off current, the overall path current? This one determines the current. So if we have the situation like this one, then which one determines the current? This one determines the current. So simply speaking, if we have two different devices having different levels of off current, then you can easily understand the overall path current will be determined by this guy, which has lower leakage current. So simply speaking, when you evaluate the transistor 1 current, which seems to be always, so its source is grounded, and nth current which have the source to body values corresponding to Vx. Then when we say that IN1 and IN2 should be identical because they are serially connected, then you can find that the sub-threshold current is not exactly given by this exponential to something, but this is relatively complicated behavior. But please note that I told you that this eta and k, they are all uniqueness quantities and much lower than 1. So simply speaking, starting from this 1, they becomes relatively small contribution, and this upper part we have eta plus k, and here we have 2 eta times k. If eta is not that high, then overall this factor becomes quite close to 1. So simply speaking, now we can say that our subthreshold current is given by 10 to the s minus eta VDD. So this uh, additional factor can be easily neglected or approximated as 1. And now you can see that if we have such a case, the current is relatively smaller. Okay. Are you all with me? I mean that if you have just N1 transistor only, then what will be your value for up current? In this case, your gate voltage is 0 and your drain voltage is VDD, and your source to body voltage is all 0. So this guy, and another guy all becomes 0, and your current will be just originally I off. However, when we just make a stack of 2 serially connected MOSFET, then compared with our original I off current, we have additional factor. And this additional factor is certainly lower than or smaller than 1 because it has negative sign here. So typically, for certain case, let's just say that VDD is roughly 1 volt, and eta is roughly also, for example, 0.1, and S is also roughly 100 millivolt per decade. Then what will happen? This product will be just 100 millivolt. So we know that this overall calculation will be give us just 0.1. Okay, are you with me? Because once again, let me just repeat. This one, the typical value for certain device can be 0.1, and it is around 1 volt. Nowadays 0.7, but whatever. This is just a range of 1 volt, and this is nowadays more or less close to 60 millivolt. How about 100? So when we combine them all, then you can find that when we just make a stack of 2 transistors here and there, amazingly our current conduction can be, or leakage conduction can be reduced. So it is in some sense it is counterintuitive because when we have 2 transistors, then maybe we can expect, oh, since transistors are twice more, then maybe we have twice more leakage current. However, they are serially connected, and in the case of serially connected devices, the leakage current is determined by the worst one. Okay? Here worst means that which cannot conduct the current least. Okay, so now let's go to the next part. So therefore when we have this stack effect, then we can have a relatively low static power consumption. Up to now, we have thought about the sub-threshold leakage current, but another important mechanism is gate leakage. So gate leakage, let me just draw once again. Here we have metal. So previously it was a polysilicon, but nowadays it is metal. And let's say that here we have silicon substrate. Yes, and here we have oxide layer. This is quite thin. So thin, like just a few nanometer thick here. And now let's say that we have applied quite high voltage. For example, let me just go to this case. Here, these are all measurement result. I mean that here we have 29, means that 29 angstrom. Let's say in this specific case we have 22.9 nanometer thick pure oxide, and here we have in this time there was no metal, so this is maybe poly, but let's say that this is just a gate and silicon. And now we have applied, for example, 3 volt. Wow, that is a huge amount of voltage. But anyway, we have applied 3 volt. Then what happens? If you apply this very thin oxide 3 volt, then we will get the current whose level is corresponding to 10 to the minus 3 ampere per square centimeter. Okay, so since this is positive and negative, actually you can expect the current direction of your current conduction in this way. Okay, because this is positive and relatively negative, so there will be current conduction in this way. However, this is the direction of current, and in reality, what happens in this case is quite obvious. Here we have many electrons, inversion electrons, and since we have applied so high voltages, 3 volt, and these electrons are attracted, so they just overcome this oxide layer and jump into gate. So this is shown here, and when electrons are moving this way, in terms of current conduction, since the electron carries negative charges, so current flows in this way. And although I have drawn just like a direct jump from silicon channel to the gate, but there may be some different options, like instead of directly jumping to this one, we can have some intermediate position and jump. Okay? So there can be many different ways. That's the reason why we have various physical mechanisms to allow the current conduction between gate and silicon channel. Of course, I'm not saying that between this gate and silicon channel we can have the normal current conduction like in the silicon channel. There are many electrons, and when we apply certain voltage, and they are moving. It's not like in silicon channel. It is just quantum mechanical tunneling into certain defect inside the oxide, and once again come to the gate part. So because we have applied quite high voltage, relatively high voltage to our gate. So what we can expect is quite obvious. Starting from this 3.6 nanometer thick one, what is the value? You can see that its value is 10 to the minus 5. However, when you just decrease this 3.6 nanometer thick into 1.5 nanometer thick oxide, it is easy to make it. Then the expected leakage current is orders of 10 to the 3. So when compared with this original value 3.6, you just reduce the oxide thickness by amount of 2.1 nanometer, and what you get is, what is it? What you get is 8 orders of magnitude increase of your leakage current. 8 orders of magnitude means that 100 million times larger leakage current by thinning your gate oxide. So simply speaking, when you make any mistakes, when you make your gate oxide, sometimes your oxide thickness can be slightly thicker and slightly thinner, then that will introduce a huge impact. For example, let's say that so please note that here we have just 1 angstrom difference in its thickness, but change is really visible. And here you can see that we have 20 and 15, and this is just 5 angstrom difference. 5 angstrom difference introduce about 100 times different gate leakage current. And what is the 5 angstrom? Everybody in this classroom may understand 5 angstrom is just a lattice constant of unit cell of our silicon crystal. Just one unit cell has a size of 5.43 angstrom. So if you just make your silicon dioxide 1 unit layer thicker or thinner, then you will have 100 larger leakage current or more than 100 lower leakage current. So simply speaking, it is an extremely strong function of dielectric thickness, and it is ever increasing. So its message is quite straightforward. Do not scale down your oxide. This is prohibited because, of course, when you decrease your oxide, then positive effect is, of course, you have inversely increasing oxide capacitance, and oxide capacitance is the most important quantity when we consider CMOS technology. So we have some desires to decrease oxide thickness. However, this graph just shows that eventually this gate leakage will become so-called show stopper. So our device scaling will be eventually stopped by this gate leakage. That was our previous problem. However, engineers find ways. So that was 65 nanometer technology, so former technology. And here, as I told you many times, at that time we have used polysilicon as a gate material, and here we had pure silicon dioxide as gate oxide material. However, now in newer technology, we have introduced, actually the guys in Intel introduced metal gate and high K oxide layer. Simply speaking, what is the difference between this pure silicon dioxide and high K material? I mean that in the case of silicon dioxide, we usually say that relative permittivity of silicon dioxide material is about 3.9. Okay, so yes, so therefore when we have, for example, certain amount of thickness, then our oxide capacitance will be given by 3.9 times the permittivity of our vacuum, and divided by what? Divided by the Tox. So although our goal is to increase this oxide capacitance, since material is given, so what we can do was just to reduce the thickness of oxide. Make the oxide thinner, then you will get higher capacitance. That was the previous situation. However, as I told you before, if you reduce this oxide thickness too aggressively, then the leakage current becomes the showstopper. Your gate leakage will become too high, so your device or your logic circuit cannot survive any longer. So what they did is, instead of decreasing this oxide thickness to increase oxide capacitance, instead of that, keep this number. On the other hand, just to increase this number. So by introducing a new material which has relatively higher permittivity. This is hafnium oxide, and using the hafnium oxide layer, which has the relative permittivity higher than 20, then they can make it. I mean that if you have, for example, let's say that this is close to number 4, and although this is higher than 20, but let's say that just 20, then let's say we have 5 times higher relative permittivity. Then what will happen? If you keep the same oxide thickness, then you will get 5 times higher oxide capacitance. But in reality, we do not scale that way. Instead of that, we increase oxide thickness significantly and use high K material. Then we can keep the Cox value in a reasonable way, but drastically reducing the gate leakage current. That is the situation. So previously, so we have already seen that the major component of leakage current is subthreshold current and gate leakage current. compared with these two terms, the junction leakage is negligible. However, by introducing this high K metal gate, then we can say that the problem of leakage current can be more or less resolved. So the static power is solely determined by nowadays sub-threshold current. So that's the reason why we are always talk about the sub-threshold leakage current. So are you all with me? So now
근데 옥사이드 캐패시턴스가 증가하는 게
Mhm.
어드밴티지라고 하셨는데
yes.
어떤 부분에서 어드밴티지?
Okay, so that's a good question. Thank you for your question. And I understood that we are all striving to increase oxide capacitance. So let me just come back to our very basic long channel MOSFET expression. So C ox W over L, and we have blah blah blah, which depends on VGS and VGS. Depends on operational point. We have different values. Point is here we have Cox. Simply speaking, if you have higher oxide capacitance, then you can get more electron. Let's think about this. Let's make a comparison for these two different technologies. One technology has a relatively high oxide capacitance. Unfortunately, another one has a relatively low capacitance, and we have applied VGS and VG and VG, and substrate is just grounded. Then let's assume that also our threshold voltage is the same. So for one case, the amount of charge we can get, Q inversion, will be simply given by oxide capacitance minus VGS minus threshold voltage. So simply speaking, when you have high oxide capacitance, then you will get more inversion charge. However, if you have a relatively poor technology which has a lower oxide capacitance, then even though you have applied the same amount of voltage to your device, then your collected inversion charge density will be lower. So from the viewpoint of performance, so once again, performance is same word for the I op in our case, I, not I op, I on. In order to maximize this I on, we must have the maximum oxide capacitance we can achieve. So therefore we always try to decrease oxide thickness, but that was just prohibited by this significant gate current increase. However, that problem was solved by very talented engineers by introducing high K material, and now using the high K material we can make this oxide thickness quite thick. So since all of these operation escaping from silicon channel, jump into this oxide layer and eventually go to this one, it is critically dependent on thickness. If we have quite thick gate oxide, then although we have applied high voltage, but that will be significantly reduced. So simply speaking, that's it. So we have solved that problem by introducing a new material. Of course, introducing a new material is not that easy. It always costs quite a lot. So $1 billion are used required to change a certain material, and long time is required. For example, the recent progress is like this. High-K metal gate was already introduced in logic gate 2 decades ago. So it is around 2000 introduction. What happens our DRAM? In DRAM, it was just introduced a few years ago. I mean that DRAM guys know that high-K metal gate introduce quite good advantages when we consider in terms of COX. They also wanted to increase COX eagerly. However, when we introduce such kind of a high-K material into DRAM, then we can observe all kinds of problem not expected in this DRAM field. So that's the reason why engineers are sometimes very conservative to introduce new technology, new material. But eventually, when they are pushed at the end of their resistance, then they give up, then just introduce new or adopt new material. Then something innovative things happen once again. Okay, so in this last slide, here we have 2 slides, but I will quickly cover this one in the next lecture, and we will move to the discussion on the interconnect. Okay, thank you for your attention.